So the next thing that we want to do is get a more sort of a global, a broader perspective on the relationship between the properties of a function, the graph of a function, and the properties of its derivative. What this is going to do is let us do a process that we can think of as curve sketching. What curve sketching is it's a way for us to take information about the derivative of a function and transform it into, relate it to information about the function itself. So what I'd like to do, for starters, is come back to my notes here. So we decided that the derivative of a function tells us the slope of a tangent line to its graph. It tells us the rate of change of the dependent variable of that function per unit change in the independent variable. And this is where we want to really get a hook into our next piece of material, it tells us how exactly, at what rate, the function is increasing or decreasing at each of its points. So in particular, let's go look not at our demand function, but let's take a moment and transform our demand function into a revenue function instead. So to do that, we have to know, first of all, what is the definition of revenue? Sales revenue, as you might know from your other management courses, sales revenue is a way to quantify how much money that we make by selling a quantity of our product at a certain unit price. So if I, for example, am going to sell 800,000 units of my product at a unit price of $264.31. My sales revenue is my total amount of money that I collect from that sale. And that's going to be, by definition, equal to the price per unit multiplied by the total number of units that we sell. So revenue is nothing more than price multiplied by quantity. Well, what does that mean for the project? Quantity is our independent variable. It's Q. But price, meanwhile, is the output value in the demand function. So our revenue function can be gotten by multiplying our demand function d of q by another power of q. And so at the level of the algebra, if I want my revenue function, what I should be doing is I should be taking my demand function, minus 0.00027 q squared plus times q plus 558.223. Just by taking that demand function, I'm actually just going to write it down. So here was my, here is my demand function, minus 0.00027 q squared minus 0.14873 q plus 558.23. This was my demand function. Remember, this is just price. That's what d of q tells me. So if I want revenue, what I really need to do is I just need to multiply that price by quantity, P times Q, D of Q times Q. Multiply this whole thing by another power of Q, and that's going to give me my revenue function. Now, what's going to happen when I multiply all of these terms by Q, just distribute this Q into all three of these terms, is that all of my powers of Q are just going to go up by 1. So when we look at the revenue function, it's not going to look that much different than the demand function, but the exponents on the q's go up. So it's q to the third power, q to the second power, and then we have a q to the first power that shows up on this 558.23. So that's how we can get a formula that describes my revenue function. How much money am I going to make in sales by selling q many of my product, right? And we can do that with the formula, and not just with each of my data points, because now this tells me for any quantity that I can choose in the world, not just the ones that are computed from our test markets. What is my sales revenue, total amount of sales revenue, going to be? So when our demand function was quadratic, polynomial of degree 2, our revenue function, we multiplied by another q, ends up being a cubic, a polynomial of degree 3. So there's where we can get a revenue function from. So here's a graph of our revenue function. Again, we got this revenue function just by multiplying our demand function by q, so that all of the exponents end up just going up by 1 to give me my revenue function. So the question in decision report 3 is which of the test markets, so your test markets each had different quantities on the national market that they corresponded to. Which of your test markets is going to correspond to the potentially the highest value for revenue? Notice that this revenue function does something that the demand function did not. The revenue function goes up for a while, and then it reaches a peak, and then it goes back down. This makes some sense because if I charge $0, sorry, if I charge $0 and I try to give away my product, then I'm going to make 0 sales revenue. But similarly, if I price myself out of the market by charging so much money for my product that nobody buys it, I also am going to make 0 sales revenue. So there are kind of 2 different ways to make 0 revenue: by charging so much that my quantity goes down to 0, or by charging so little that I'm giving away a maximum amount of my product. So price is equal to 0. So the revenue function goes up and then it goes down. And a valid question to ask is, where is my sales revenue reaching a maximum value? So to figure out how to untangle that question, what we want to do is look broadly at how the properties of this graph of a function, the revenue function in this example, relate to the properties of its derivative. So you notice, first of all, that in the left-hand part of my graph, where my revenue function is increasing, my green curve is going up from left to right. Where my revenue is increasing, all of my slopes are going to be positive. All of my purple tangent lines here are increasing as we go from left to right. So they're going to have a slope which is a positive number. So the first takeaway for us is going to be that when a function is increasing, its derivative is a positive quantity. I've put in our live textbook a link to this cool little simulation. The simulation lets you kind of sketch the graph of a function, f of x, and underneath it, it shows you what the graph of the derivative of that function is going to look like. So first of all, when my function is just a straight horizontal line, my derivative is 0 everywhere. That's something that we already observed from later on. But if I create some interesting behavior in my original function graph, then we can see that the derivative actually has some interesting qualities as well. And where this function is increasing, here we go, where this function is increasing, where the blue curve is going up, those are all places where the derivative is positive. It's above the x-axis. Right? So where the function is increasing, the derivative is positive. It's above the x-axis. Similarly, where the function is decreasing, as it is in this realm over here, where the function is decreasing, where the blue curve is going down, all the values of my derivative are negative. They're below the x-axis. So that's, of course, the flip side, that where my function is decreasing, its derivative, f prime, is negative. So when f is increasing, f prime is positive. When f is decreasing, f prime is negative. Again, this too comports with our ideas of slope, that lines with positive slope are increasing from left to right. Lines with negative slope are decreasing from left to right. This just takes that from a statement about lines to a statement which can be true about curves, just by thinking about the slopes of their tangent lines, in other words, the derivative. So this is a cool little interactive that we can sort of mess around with graphs and watch how the values of the derivative happen to change. We also notice that if I try and stretch this graph so that we get steeper and steeper increase, so right here, for example, is a really steep place where this function is increasing really rapidly. We find out that its derivative turns out to be really large and positive at that point. So the steeper my graph, the larger the value of its derivative, whether it's a large positive, as it is over here, or maybe a large negative, as it is over here, where it's decreasing really rapidly. Now, for the sake of the project, we're going to be interested not just at places where our functions like revenue, cost, profit are increasing or decreasing, but we also want to zero in on how to find out where those functions are reaching maximum or minimum points. It's a process that we call optimization. How do we find out where a function like revenue, to skip back to our revenue graph here, how can the derivative tell us when we have reached the top of the hill? So what is the derivative of this function going to be if I'm up here at the maximum value of revenue? Well, at a maximum of a function, so at this top of the hill in my purple graph, for example, or even at the bottom of this valley in my purple graph at a minimum, what those 2 points have in common with one another is that at those points, my function is neither increasing nor decreasing. Why is that? Well, that's because at those points, my tangent line, can't quite get it exactly to line up here, but at the top of my hill here, my tangent line is neither going to be going up nor going down in slope, right? My tangent line is going to be horizontal. So the observation here is that at those points, my function is neither increasing nor decreasing. So I could maybe even say here, the tangent is horizontal. And so if I have a horizontal tangent line, then the slope of that tangent line is going to be the slope of a horizontal line. And the slope of a horizontal line is 0. So those places where a function has what we call a local maximum, or the top of a hill, or a local minimum, the bottom of a valley, at those places, the derivative is going to be equal to a quantity which is neither positive nor negative, which most often means that the derivative is going to be equal to 0 at that point. So we call these points critical points. A critical point, by definition, in calculus is a point where a function is neither increasing nor decreasing, which, as long as the derivative is able to be defined at that point, means that the derivative is equal to 0. We could also have a situation where the derivative is undefined at that point, but this is kind of rare. We're not going to see it in our course, but just to kind of put that out there, that a critical point can also talk about a place where derivative is undefined. So here we have this nice sort of classification. It tells me that the derivative, the value, the sign of a derivative, whether it's positive, negative, or 0, tells me whether or not that function itself is increasing, decreasing, or neither. And a local maximum or a local minimum can occur only when the value of the derivative is 0 or undefined at that point. So why this is nice is that saying that the value of something is equal to 0 gives me a recipe. It gives me an equation that if I have an equation for this derivative, this derivative function, I can use this observation to then solve that equation and figure out where these local maxima or local minima might be happening. So let's take a look at what that looks like in practice. I'm going to go to a simplified version of our revenue function. So this one's got some sort of nasty coefficients in it. So I'd like not to use those nasty coefficients if we can avoid it. Let me just come up with a simplified version that we can look at together. Let's do, no, I don't want that. I want 12. Maybe I'll put a minus in front of this and a plus in front of this. All right, so I'm just going to simplify my function here a little bit. Maybe I'll also add a constant. Okay. So here's a function, y equals x minus x cubed plus 12x plus 10. And my question is, where is this local maximum going to be located, which my grapher here is helpfully telling me exactly the coordinates, negative 2, 26. And then also, where's my local minimum? Negative 2, negative 6. Well, okay, the graph is telling me that. But let's actually do the work. Let's actually use the observations that we made here, which is that if I want to find out where local maximum and local minimum points occur, I should find out what is the derivative of my function and then figure out where that derivative can be equal to 0. Let's actually implement that observation, and then this will be where we wrap up for today. So I want to find, using calculus and algebra, the locations of these local minimum and local maximum points. So to do that, I want to know, first of all, where my function is experiencing a critical point. Where are the critical points? Remember, critical points mean places where the function is neither increasing nor decreasing. These are the points where f prime, the derivative, is neither positive nor negative, which for our purposes, where our function has a derivative that's defined everywhere, for our purposes, that's going to mean places where the derivative is equal to 0. So anyone who's been through a calculus course will remember this trope very well. We do a lot in calculus of taking a derivative, but then also setting that derivative equal to 0 and solving for x. And we do that because that's the strategy for how we figure out where these local maximum and local minimum points on the graph of a function are. They can only happen at points that are critical points. So what that suggests is that the first thing I should do is find the derivative of this function. We can do that using the power rule. I've got a constant over here. I've got x to the first power there. I've got x to the third power there. I can take the derivative of each of those pieces separately according to the linearity theorem. The derivative of my constant is 0, as the derivatives of constants always are. The derivative of my x to the power first, using, again, the same power rule. Multiply by the exponent, 1. Decrease the exponent by 1, 1 minus 1. That's going to give me 0. X to the power 0 is just going to give me 1. So that derivative is just going to be 1. For x to the third power, using the power rule, we'll multiply by the exponent. That's going to give me a 3. And then we'll decrease the exponent, the third power, by 1 to get x to the power 2. So there are my 3 pieces, and then I just have to use linearity to piece them back together. I'm running out of space over here, sorry. So I'm going to get a minus in front of this one, plus 12 in front of this one, plus 10 in front of that one. Simplify that all out, I'm going to get minus 3x squared plus 12 plus 0, which I don't have to write. So there's my derivative. My goal, remember, is to figure out where are the places where this derivative is equal to 0. Now that I have a formula for this derivative, I can set that formula equal to 0 and solve for x. And fortunately for us, I've kind of arranged the algebra so that it's not too terrible. If I want to solve this for x, I can, let's see, divide everything by -3. X squared minus 4 is equal to 0. And then maybe I'll factor the left-hand side, just because factoring is fun. We could have solved this in any number of other ways. But then split this factorization into 2 because we have a 0 on the right-hand side. And we end up with 2 solutions, x equals 2 and x equals -2. And sure enough, that exactly comports with the x values of the local maximum on this graph and the local minimum on this graph. So, okay, we found the critical points, x equals 2, x equals -2. The question then is, okay, we know that that's where our local minimum, local maximum points can happen. How do we know which one is which? Without having a graph in front of us. We have the benefit here of actually having the visual, so we know that x equals 2 is going to be the max, x equals -2 is going to be the local min. But is there something that we can do that can show us that without having to have a graph in front of us? And this is where we'll wrap up for today. So how I like to do this is I like to actually take this derivative function, -3x squared plus 12, and think about what its graph looks like. So I'm going to take off the work here on the board in just a second. And then we're going to also put on a graph of the derivative function so that we can see how it tells us the story about which one is a local min and which one is a local max. Let me take a moment and just change my viewing window here just so we can see a little bit more detail. So I'm going to go -10 to 10 on the x-axis. Yeah, there we go. So let's graph the derivative function. We decided that was -3x squared plus 12. Graph that in purple because it aligns with the purple that we just used. All right, so here's a graph of the derivative. That's the purple graph. And what we notice is that there's 2 places at which that derivative graph crosses the x-axis. Right? At those points, the derivative was equal to 0. And the derivative was equal to 0 because those are the points where the original function had a horizontal tangent line because it was a local maximum and a local minimum, respectively. But if our goal next is to know for sure whether or not each of those points was a maximum or a minimum, to be able to tell that story, here's how I like to do it. I just like to go back to this interpretation table. Right? It tells me that wherever the derivative is positive, my function is increasing. Wherever the derivative is negative, my function is decreasing. And then I'm just going to sketch that information about the derivative right here onto my graph. So we're going to imagine that we can't see the red graph for a second. And we're going to use this information to tell me something about what the red graph would look like, even if we didn't know what the red graph looked like to begin with. So how I do that is I'm going to look at each of the places on this derivative graph and look to see where the derivative graph is positive and where the derivative graph is negative. The derivative graph is positive everywhere here in between x equals -2 and x equals 2. So I'm going to kind of highlight that on the x-axis. So in here, the derivative is positive. F prime is positive because the graph is above the x-axis. But then using our correspondence, that means that we know that the function is increasing. So So I kind of like to draw that information right there on a little number line, right? Where the derivative is positive, the function is increasing. And then similarly, everywhere else, so if I highlight the other parts of the x-axis, everywhere else, this derivative is negative. The graph of the derivative function is below the x-axis. So everywhere else, f prime is negative. And where f prime is negative, according to our little chart of correspondence, that means that my function f, the graph of f, will be decreasing. So negative and decreasing on this side, and then also negative and decreasing on the other side. Slip that in there, decreasing.
That's just a snowblower.
So at the end of the day, if the question is which of these 2 points, x equals -2 and x equals 2, these are my critical points, these are the places where my function is neither increasing nor decreasing, which one is a local minimum and which one is a local maximum? Well, we can spot a local maximum as a point where a function changes from increasing on the left to decreasing on the right. When I reach the top of the hill, I go from increasing to decreasing. So because of this change from increasing on the left to decreasing on the right, we know that that point is going to be a local maximum of the function f. And for the same reason, when I switch from decreasing to increasing, we end up with a local min of the function f. This is what's called the first derivative test. And it's my favorite way of figuring out whether or not a critical point is a local maximum or a local minimum, just based on what the first derivative of the function is telling us.
I gotta get the snowball. Stop.